Right, good afternoon. Thank you so much for joining us here at the National Space Centre on this day where we celebrate the anniversary of the first science images being released from the James Webb Space Telescope. We're very fortunate to have our three researchers from the University of Leicester here joining us to actually give us a little bit more of an insight into some of the images that were released over this past year and some of the data that's also come back from the James Webb Space Telescope. So I'm going to get our panelists to introduce themselves to us so we understand, I guess, where they work, what they're doing, and how their research relates to the James Webb Space Telescope. So, Henrik, can I maybe ask you to start off?
Yes, of course. My name is Henrik Melin. I'm a research fellow at the University of Leicester, and I use the James Webb Space Telescope to investigate the giant planets in our very own solar system.
I'm Sarah Casewell. I'm an observational astronomer, and I research stars and exoplanets. So I'm looking for planets around other stars, and I'm looking to find out what they're made of, what's in their atmospheres.
And I'm Nial Tanvir. I am a professor of astronomy here in Leicester, and I work mainly on exploding stars, many of which are very far away across the universe, so sitting in some of the very distant galaxies that we'll be having a look at later on in the presentation.
Perfect. So we've got a real mix of expertise on our panel this afternoon. And before we share some of the images that have been brought back from the James Webb Space Telescope, we thought we'd just begin by a little bit of an introduction about the telescope and why it's such an important telescope that's been launched into space. So in December the 25th, 2021, the telescope launched aboard an Ariane 5 rocket. It was a very, very good launch, perfect as some of the scientists were saying. It launched into space carrying the James Webb Space Telescope folded up in its nose cone. So when it was released in space, the telescope started to unfold, and you can see the process being kind of taking underway here. It spent about 6 months in its what we call commissioning phase. So it was, number one, deploying, unfolding, but also some of those instruments and equipment were being tested out and calibrated, ready for that science operational phase to begin. So in July of last year is when that science phase began. But we can have a look a little bit more at the telescope and its design. So we can see that the front side, the observing side of the telescope, is made up of the primary mirror. It's constructed of 18 hexagonal pieces, and we've got just one. Yeah, thank you, Sarah. Behind our panelists there, that's the size of one of those 18 mirrors, and you can see 18 of them form the primary mirror to begin with. Light is kind of collected on that mirror, reflected back onto what we call the secondary mirror, before it is then bounced back through the tiny gap in the primary mirror, through the detector, to the science instruments that actually sit behind. You've got that multi-layer sun shield about the size of a tennis court, designed to keep this telescope cool. It's an infrared telescope, so it's detecting light that we cannot see with our eyes beyond what we call the red end of the spectrum, so that infrared light, or heat as we better know it. And that means that we need to keep the telescope cool, its instruments cool, to be able to detect the infrared light from things out in the universe rather than the heat from its own instruments. On the sun-facing side, you can see a few other bits. It's got its solar power array, so using the sun's light to help give it the energy it needs to work. You've got the communications antenna there as well, and then you've got a star tracker helping to actually guide and position the telescope coarsely, and then that steering as well. But the instrument panel that sits behind the primary mirror of the Webb telescope, it doesn't just contain one instrument. It contains 4 different instruments. You've got NIRCam, which stands for the Near Infrared Camera. You've got NIRSpec, the Near Infrared Spectrograph, which basically means it's splitting out the light into its different wavelengths so you can analyze them a bit more carefully. You've got MIRI, the mid-infrared instrument, and there's a lovely connection to the University of Leicester that hopefully some of our panelists will describe, and then you've got the fine guidance sensor as well. It's important to realize that just like when we see visible light and we split that into the colors of the rainbow, we do the same with infrared light. So we have near-infrared light, mid-infrared light, far-infrared light, and all those different types of light can tell us something different about the universe and what we're seeing, just like different colors of visible light can tell us something different about what we're seeing with our eyes. So on that note, we've got a few of the different images here from the past year, little bits of data collected by the Webb Telescope to help tell us things about our cosmos, our solar system. So we're going to hand over to the panelists in a sense to perhaps get us started and shed some light, I guess, on why these images are really important and what they actually show. So I think maybe we'll start off with our barred spiral galaxy, if that's okay. And if there's any particular one of our panelists that wants to describe, I guess, the importance of this image or what it's showing, that would be awesome.
I'll pick up on this one then. So this is a galaxy, and what is a galaxy, you ask? Maybe many of you know, but maybe not everyone knows. A galaxy is a gigantic collection of stars, billions and billions of stars. We live in a galaxy, it's called the Milky Way, of course, and because we're in the middle of the galaxy, we don't get a great view of our own galaxy that looks like this. In order to see a galaxy with all this spiral structure like this one, you need, of course, to be seeing it from outside, and this is a galaxy that's about 40 to 50 million light years away from us. Because of the fact that you have within this galaxy, like I say, billions of stars and a lot of gas and dust as well, when you look at a picture like this, you're sort of seeing the accumulated light. You're not really seeing the individual stars there. So you're seeing their accumulated light, and you can see how it makes this lovely spiral pattern. And you're perhaps thinking, okay, what makes that spiral pattern? Good question. Still a sort of topic of research. It's not that the stars are being sort of flung out, as you might think, and it's not because they're being sucked in either into the middle, as you also might think. Actually, they're kind of going round and round, but the ones in the middle are going round faster, and so it sort of smears out this pattern. The ones at the outside are going round slower, and so they get sort of trailed back. Now, the thing about this picture, which makes it a bit different from pictures of galaxies that you might be used to, is that it is taken in the infrared light that the JWST is particularly powerful in observing. And so that means that the dust, and by dust we kind of mean it's like smoke. It's residue from stars. It's little tiny particles which are similar in size to smoke particles, and they're very tenuously distributed throughout space, much more tenuous than in a bonfire or something like that. But because there can be light years of these particles, they can make quite thick clouds. It can be hard to see through them. And in normal light, if you look at a picture of a galaxy, quite a lot of it is obscured by these clouds of dust. And they help make the pattern, but you don't really see all of the light that's there because it's being blocked by this dust. In the infrared, we see much more through that dust. So it's a bit like firemen using infrared goggles to see through smoke when they enter a building. And so we get a sort of better sense of the complete picture in a way by looking at this infrared picture. And you can see that not only have you got that spiral pattern, you've certainly got a kind of sponginess to it as well. The sort of holes and gaps that you kind of make out in this spiral pattern. And that's really where you've got the sort of activity of star formation and star death. Stars that are being formed, particularly in those red blobby areas that you see, and then some of the bubbles will be created by exploding stars that exploded some time ago and have blasted a sort of hole in the gas of the galaxy, and that ends up producing that kind of slightly bubbly appearance. If this was our galaxy that you were looking at, the sun would be somewhere, towards the edge of this. We're not in the middle of our own galaxy. We're kind of nearer the edge, although not right at the edge. So I think this is quite a nice picture because later on we will be delving, on the one hand, into our own galaxy and looking in more detail at some of the sort of features that we can see in this galaxy, but within our own galaxy. But we'll also be looking at some other galaxies that are far, far away across the universe. And so this is just a nearby example to get us into the idea of what galaxies are.
Thank you. So a lovely look at, I guess, a nice galaxy, similar in sense to ours as a spiral galaxy, but it's within these galaxies that we start to find other very interesting things that the Webb Telescope has been looking for. So perhaps next we could have a look at a very famous image as taken by Hubble, but actually the comparison compared with what the Webb Telescope was able to capture. Sarah, would you be happy to give a little bit of an insight into what we see here?
I can talk about this. So this is the Orion Nebula, and on the left here you have the image from Hubble, which is an optical image. I'm actually going to stand down here so I can point without sitting on Henrik. And it's an optical image, and you can see from what Nial was saying about the galaxy, we have the same thing. We can't really see very much on the left. We have these big fingers of gas, but we can't see what's going on in there, and that's because there is dust obscuring what we're looking at. We're essentially looking into a cloud. But if you look at the image on the right, which is the image from JWST, you can suddenly see all these stars in the background that are not visible on the left-hand side image. And this is because in the infrared, we can see through all that dust to the stars that are in the background. So the Orion Nebula, if you're familiar with the night sky at night, you might be able to identify Orion. It's a very well-known constellation. It has these 3 stars across the middle for Orion's belt, and further down there is Orion's sword, and the slightly fuzzy patch you might be able to see around the middle star on a good night is where this is located. And the fingers on the right you can also see they're obscured with still some more gas and dust, but the thing I think that was surprising for a lot of astronomers when this image came out is that we expected to see lots of stars still forming. This region is only a few million years old, which is very young as far as stars are concerned. And looking at the tips of these sort of fingers, there isn't very much star formation. So this tells us that the star formation is already finished in this area of our own galaxy. I think in the middle one of the 3, you can see there's sort of a red point with a newly formed star in it. So that was quite surprising. And thank you, Dhara. So you can see the red bit there is where there is a newly formed star that is just breaking out. Thank you. Just breaking out of the gas and the dust, and there are a few more here on the edges. But this sort of ridge is where the star formation would have happened, but we think it is now finished. Yeah, I love this image. I love this image just because I remember the first Hubble images of this as well. So having this direct comparison is just stunning.
It definitely gives us an idea or a sense of why the Webb Telescope has been so important, not just because it's a bigger telescope, but because it has different eyes. It allows us to see some of the things that we previously weren't able to see. Any other comments from our panelists on this, or should we move on? Let's move on then. So as we mentioned, this is a star-forming region, and our sun would have formed in a nebula very much like this. And of course, now we see around our star lots and lots of planets. And we think of the Webb Telescope as a telescope that's looking out into distant space to these distant galaxies like Nial was talking about. But actually, it's looking in our own cosmic backyard as well. And there is a stunning image of Jupiter that was revealed. And actually, Henrik, you're the perfect person to talk about this. So can you give us an insight into what Webb is showing us here?
Yes. Well, first of all, the Webb was obviously designed to see the first galaxies in the universe. That means that the telescope is extraordinarily sensitive. And so pointing the telescope at Jupiter is a daring thing to do. Jupiter is one of the brightest things in the night sky. And so it's actually quite difficult to observe Jupiter with the Webb telescope because it's so bright. And but here's one example where it works. You know, some instruments, Jupiter will saturate, so we can't see very much. But here's an image taken with near cam. And this is really a wonderful tour of the whole Jupiter system. Of course, we have Jupiter right in the middle here with iconic belts and zones, these fierce atmospheric sort of currents running along constant longitude, east and west. We also have the Great Red Spot. That's the largest storm in the solar system. You can fit the entirety of the Earth inside that storm. That kind of tells you how large these planets are, right? These are enormous balls of gas. And there's lots of interesting stuff happening too. You can see basically the northern lights and sort of bluish up there, sitting slightly above the atmosphere, is something that happens at really high altitude. It's also see it in the southern hemisphere, the southern lights or southern aurora. One really fascinating thing about this image is you can see the rings of Jupiter. It's a little hard to see on the screen with the light on it, but you can see the rings going right there, and you don't really think about Jupiter as a planet with rings, like Saturn, right? But here they are, because the telescope is so incredibly sensitive, it just pops out. You can just stare at Jupiter for like, I don't know, this is probably 5 seconds, and they just pop out, just like that. So we also have shepherd moons, like Adrastea, some minor moons and things like that. It's a beautiful image of Jupiter, and it's an image in wavelength we're not used to looking at, really. We're used for Hubble images, where we see different processes happening because we're looking at different colors of light, effectively. And so I'm studying the northern lights of Jupiter. That's sort of my thing. The northern lights of the giant planets in general. And to see it with the Webb Telescope popping out like this is extraordinary. There's so much work to be done with just this one single image. So lots of work to come, but I'm really excited about it. So yeah, thank you.
Thank you. It's a novel and a different look at a planet that we are also very familiar with, but it's lovely to see, like you mentioned, some of those features that we're not really keen on seeing or used to seeing, like those rings actually popping out. I'm going to open it a bit more up to our panel now. So we've talked about galaxies, we've talked about nebulae in these star-forming regions, the planets in our own solar system. But actually, is there anything that you guys particularly would like to share while we've got some of these images up? Yeah, which one would you like to go to?
So the one that's called gravitational lensing, I think would be a nice one. Okay, so there's quite a lot to unpack in this picture. There are a few of the pictures that we might look at that are rather similar and similarly interesting. So let me tell you what we're looking at here. So you see a lot of blobs on this picture. These blobs, apart from the ones with 6 or 8 spiky points, those are stars in the Milky Way in our galaxy that just happen to be in this part of the sky. But what we're really looking at, what the telescope was interested in, are the distant fuzzy blobs, which are all distant galaxies. Some of them look a little bit spirally, like the one we saw earlier on. Some of them look rather more blobby, and that just reflects the fact that you get different kinds of galaxies. Some are sort of smoother, don't have that same spiral structure. Some do. And as you go further away in the universe, actually you find galaxies tend to look a bit more erratic, a bit more irregular. But what you'll notice about these ones in particular is that they're clustered in the middle. And what this is, in fact, is an example of what we call a galaxy cluster. In some rather rare parts of the universe, you get real dense concentrations of galaxies, so-called clusters of galaxies, where you may get thousands of galaxies that are as big as our own Milky Way galaxy, and some that are even bigger. So those big ones in the middle are really massive galaxies that are several, perhaps 10 times the mass of our own Milky Way galaxy. Now, you'll see a lot of JWST pictures of galaxy clusters, partly because they're interesting in their own right. They're far away. This one is, I think, about 6 or 7 billion light years away from us. That means the light has taken 6 or 7 billion years in order to reach us in this image, which itself is astonishing. But actually, there's a reason why Webb has concentrated particularly on taking a lot of these cluster images, and that's because they also act like giant magnifying glasses and allow us to look at even more distant objects that are far beyond them. How do they act as magnifying glasses? They do so because of their gravitation. Because gravity, as Einstein taught us, bends the paths of light, it produces a lensing effect. It's not a sort of neat lensing effect, it's a bit of a distorted lensing effect, but because of the bending of the warping of space-time, it means that the galaxies that are even more distant behind this cluster end up being kind of spread out and distorted, and the pictures that we see of them, the images that we see, are even brighter And therefore, if you want to look at galaxies that are really far away across the universe, maybe more like 12, 13 billion light years away from us, looking back almost to the beginning of time, then a good place to do it is looking at these clusters. And the lensed galaxies that we're looking at then tend to be these ones. They tend to look rather reddish. That's sort of reflecting the fact that they're far away from us. They tend to be kind of drawn out into longer, thinner shapes, and that's because of this lensing effect, this distorting effect. But some of them, and the ones that are highlighted here where it says 1 and 2 and 3 there, they've been highlighted. They look rather faint and sort of, you'd barely know they were there. There were pictures on the right-hand panel that showed them in a bit more detail, but you can just about see little dots in the middle, and that's what they're like if you zoom in on them, if you blow them up. Kind of looks insignificant, but those have been highlighted because those are the most distant ones that we can see in this image. And these are galaxies that the light of which has taken 95% of the age of the universe to reach us. So we're seeing these galaxies. These were amongst the first ones to be formed in the universe after the Big Bang. And the one at the top in particular, I know it's fairly familiar to me because I was recently part of a group that wrote a scientific paper on that one at the top. And you think to yourself, well, that looks hard to write a scientific paper about just a little blob. What did we say? It's a little blob. Well, in fact, what we did, and we'll come on to this maybe later on, is we looked at a spectrum of that little blob, and we realized that that spectrum told us something interesting. Spectra tell you lots of things, and like I say, we'll come back and have a look at a spectrum later on. But just to give you a hint of what we were interested in scientifically, what we found was that from that spectrum, we could tell there was a lot of gas in that galaxy, cold gas. And that cold gas is sort of wrapping around the stars, and it doesn't affect the image very much at all, but because of the amount of cold gas, it allows us to calculate that this galaxy wouldn't have been emitting ultraviolet light out into the surroundings. The ultraviolet light would all be absorbed by that gas. And that turns out to be kind of interesting because for other reasons, we suspect that there is a lot of ultraviolet light drifting through space at that early time. And what we're saying is that at least it wasn't coming from galaxies like this, because this galaxy and some others that we looked at seem to be sort of wrapped in too much gas for the ultraviolet light to get out. So it's presenting a bit of a scientific puzzle that we're still working on, trying to understand if galaxies, if more of them are typical, if this is fairly typical and it's wrapped in this cloud of gas, how is the ultraviolet light getting out into the wider space between the galaxies, which we think it is. So I'll leave that there because we're going to come back to this theme later.
I love that just from one image there is so much that we can try and unpack. And actually, talking about what Nial said there, we're so used to with some of Hubble's very deep field images, seeing lots and lots of galaxies. But the idea here is that where Hubble's limit was kind of capped in the sense that it looked at visible light and into some of the near infrared, the Webb Telescope now is even able to see those further redder, more distant galaxies. So we're starting to see some of the earliest galaxies that actually existed in our universe. Awesome. Okay, so we've looked a bit at gravitational lensing and a bit more about what we see within the galaxies that Webb is looking at. Our panel, where would you like to head next, or what should we talk about next?
WASP 39b then in that case.
All right, let's find
it means I can segue quite nicely into what Nial was talking about, spectra, to be fair. There we go. So these are, in fact, spectra. This is what we get when we split up the light from, in this case, a planet. But I'm going to take a step back and tell you a little bit more about what this is. So this is spectra in 4 of the modes we use on JWST. I'm going to stand behind you this time. I've still not found the optimum place to stand. And we observed as part of the early release science program for transiting exoplanets, which I'm part of. We picked this planet, WASP 39b. WASP 39 is a planet that is about the mass of Saturn. It's physically bigger than Jupiter, however, because it's very much puffed up by how it orbits its star. I don't know what I'm stood on. I'm going to come back where I was, actually, because I don't know. I've got a weird bass noise coming. It's a bit confusing. So WASP 39 orbits a star like our sun, but it goes around once every 4 days. So it's incredibly heated on its day side, and it's quite cool on its night side. It's tidally locked, so the same side of the planet always faces the star. And it's what's called a transiting exoplanet. It was discovered as part of the SuperWASP program, which we were part of at the University of Leicester. And a colleague of mine, Francesca Feide, discovered it just after her PhD. And when I say it's a transiting exoplanet, what I mean is that the planet passes between us and the star. So as I am stood in front of this light, the light, if we were measuring the light from this square behind me, it would appear dimmer because I'm stood in front of it. So if we take an image of our star every few seconds, what we're looking for is that characteristic dip when a planet gets in the way of the light, and then we can, when it comes out the other side, you can see the light again. And if we observe at a certain point in that transit, as the planet is approaching the star, we can see through the limb of the atmosphere of the planet, and we can begin to see what the planet's made of. And that's exactly what we've done here. These spectra are looking through the limb of the star to find out what is in the atmosphere of this planet. Because what we really want to know is whether the atmospheres of these planets are like Jupiter or Saturn in our solar system, or are they like the Earth, or are they completely different? We still don't know, despite having discovered thousands of planets around other stars, how unique or not our solar system is. So studying the planets we find gives us a rough idea as to how normal or not our planets are. So you'll see there's lots of bumps and wiggles. And the bumps and wiggles are, if you can see up the side, it says amount of light blocked. So this gives you an idea where there is a lot of light blocked. There is a lot of that molecule within the atmosphere of the planet. So if you can read some of the numbers, the bottom left, the big peak that's just above Nial's head is carbon dioxide here. We have this big bump from carbon dioxide. Up here we've got some water, which we'd maybe expect. There's a bit more water here. We've got a little bit of sodium, which we knew this bit of the wavelength range overlaps with Hubble, so we already knew we had sodium from our Hubble observations. But perhaps the two big mysteries when we took this spectrum were, one, there is no methane. We see methane a lot on Jupiter. It's in Jupiter's atmosphere. We see it in a lot of those bands that Henrik was highlighting earlier. And we know that if you have carbon monoxide, CO, if you add water to it, you end up with methane, which is CH4. So you're just shuffling your C's and your H's around. And there is no methane, which was a surprise. We really thought there should be methane, and there was not. But the other mystery bump was this. Here, it took us, or over here if you prefer, it took us a really long while to figure out what was going on with that bump. And if you can see the blue line, you can see the blue line doesn't really fit it massively well. That's our model to this data. So the bump we figured out eventually is sulfur dioxide, which we did not expect to see. And sulfur dioxide is only in the atmosphere of this planet because it's created by the sunlight from its star. It's caused by what we call a photochemical reaction. So the UV and optical light from the star, it's splitting up other molecules in the atmosphere of this planet that are then recombining to form sulfur dioxide. And this is not something we have seen on planets outside of our solar system. It happens in planets inside our solar system quite a lot. We've not seen this happen in planets outside of our solar system. And this was incredibly exciting in terms of, the first spectrum of a planet we took, and it already had something we did not know about this planet inside it, which is extremely cool. And actually, we've just re-observed the planet with MIRI, the longer wavelength instrument that we built part of at the University of Leicester. So, and part of our re-observing was in the hope that we might detect more of this sulfur dioxide.
Lovely. So it's Webb not just taking lovely images, but Webb actually pinpointing some data from exoplanets, these planets around distant stars. And I know, like Sarah, you mentioned, the lines don't fit the data perfectly, but actually this still goes to show how sensitive Webb is, because there aren't any other telescopes really capable of detecting the different molecules that we find in the atmospheres of these very distant planets. So it's already starting to, I guess, resolve some of the mysteries out there with some of the exoplanets that we have.
Yeah.
Awesome. Okay, Henrik, I think it's your turn to perhaps pick an image you'd like to talk about. Where do you want to go?
Oh, it's a tough choice. Should we go to Neptune?
Oh, yes. If you hadn't have picked that one. Okay, so the question was, how many moons does Jupiter have?
Too many moons.
That's a great question. I don't know the exact number, but it's like 70 odd moons.
I think at last count it might have
50.
gone up to 95.
95. Okay.
There you go.
Thank you. Appreciate
Far
that.
too many moons. No planet needs that many moons.
So lots of moons, yeah. And speaking of moons, we can actually see some of Neptune's moons in this picture. So this is actually on the left here. It's an image taken by the James Webb Space Telescope. It's zoomed in on Neptune and its moon Triton, the biggest moon of Neptune. It's Triton itself is super interesting. It's meant to be. The thinking is that this moon is actually captured from the Kuiper Belt. Kuiper Belt? Yeah. So it doesn't form at the same time as Neptune, and it orbits in a different direction to all the other moons. But it's an interesting place, and it has sort of a thin atmosphere itself, and maybe even geological activity. But anyway, this is a zoom in of that region. If you take the whole picture, just like with anything you take with Webb, you end up with this background field of galaxies. So even though you want to take a picture of Neptune, you end up with all these galaxies in the background, which is kind of lovely, and added bonus for every picture you take with this telescope. But here is Neptune. You can see Neptune's rings. You can see the disk of Neptune with, this is the zoom in of the same thing. You can see some really bright storms of Neptune. Neptune is the furthermost out planet in our solar system, if you ignore Pluto, which I think we're allowed to do now. So it's really cold out here. It's really cold out in the solar system, yet Neptune has this fierce weather. And why is that? Well, one of the reasons is that Neptune is one of the planets with the most internal heat. And that means basically heat that's left over from the formation of the planet. So it's basically a constant shrinking of the planet which releases heat. And that itself can drive this turbulence seen in Neptune's atmosphere. By contrast, Uranus has basically no internal heat, zero, but Neptune still has weather. So there's a lot of things we don't understand. What drives weather at these planets? Another real big conundrum we don't understand about all the giant planets within our solar system, and by extension, any planet, any sort of hydrogen-based planet out there in the universe, is at the very top of the atmosphere where northern lights happen, it's much, much hotter than we expect it to be. It's hotter by hundreds and hundreds of degrees Celsius. And we don't know why. We have sunlight as an energy source, injecting energy to the atmosphere, but that can only produce maybe a quarter of the temperature we observe in the upper atmosphere. And so what I'm doing, especially with Neptune, which is so far away from the sun, I think Neptune receives about 0.1% of the sunlight we receive here on Earth. So it's extremely, extremely cold, but yet it has this fierce weather. It has this really hot upper atmosphere. So there's something else feeding this atmosphere. And that's what I'm trying to do, trying to figure out why that is. We got more Neptune data only like 3 weeks ago, and this is spectroscopy. Instead of images, we can now break the light up to its constituent ultraviolet colors. And there is some really interesting stuff in there, but I'm not quite sure about it yet, so I can't tell you for sure about it. But yeah, Neptune it's fascinating because it's so far out, it's so cold, yet it's so much stuff happening on the planet. Yes.
So the question was that Triton orbits in a different direction, and how does that work?
So if Triton wasn't formed with its own solar system, with the Neptune itself, it doesn't move in the same plane. All the moons and rings around Neptune move in the same plane, right? Basically in the equatorial plane of Neptune. Now Triton does not. It moves sort of in a circular orbit, not in the elliptical plane. I can't remember exactly what the angle is, but it orbits Neptune at a completely different angle to all the other moons. So therefore, the idea is it must be captured, a captured object from maybe in the early solar system, something happened, got knocked into orbit around Neptune. That's sort of the thinking. And that makes Triton a really interesting target as well. So by visiting Neptune, we can study, say, Triton, which is perhaps a Kuiper belt object, at the same time as look at Neptune. It's like a two for one mission, right? Which would be cool. Yes, Neptune is interesting. I'll agree with that. One fun thing about these images, it's really hard, maybe easy to tell on this one here. There is a really faint ring just inside there. I don't know if you can zoom in, Dhara. It's hard to see in this image for some reason. Just about there, you can see a faint ring. And this is, again, a testament to how sensitive this telescope is, right? In 1989, the Voyager 2 spacecraft flew by Neptune. So, what's that, 32 years ago, 34 years ago. And it did see this ring, but we've not seen it since. But just because the Webb Telescope is so incredibly sensitive, we're now seeing things. If we hadn't had the Voyager 2 spacecraft, we would not have known about this ring. And then we're seeing it with this telescope, a testament to the incredible sensitivity of this observatory. So, and sensitivity is basically what discoveries are made of, right? The more you can see, the more you can, you better your spectra, the better your images, the more you can learn about the solar system and, of course, the rest of the universe.
Yeah, 4.5 billion kilometers away, and we needed Voyager 2 to take an image of those rings, but the Webb Telescope, quite near to the Earth, able to match the same feat, I guess. Lovely images of Neptune there, really like those. Niall, I think it's about time maybe we talked about a little bit about the spectroscopy and what it can tell us, I guess, about some of the galaxies. Is this the right one?
Could we maybe go to the other one? There was
Yeah,
another
no,
one
that's
on
okay.
spectra at the top.
Which
top
one?
left.
There we go.
No, to the
No?
right of that. Yeah.
Ah,
Next one along. That's it.
there
Yeah.
we go.
Yeah. I thought this one is maybe a better one to look at because it's got a bit more about it. So what are we looking at here? So along the top is another picture. You can see a cutout of another one of those galaxy clusters with these lensed galaxies, these red, long pulled out galaxies, and one of them in particular doesn't look so elongated there, but the one that's zoomed in that says 13.1 billion years on the left, it's a little red blob. The 13.1 billion years tells you how many light years basically it is away from us. And when you put that light through one of Webb's spectrographs, you get this thing that just looks like a graph, and you think, oh, graph's boring. But what you'll notice is what this really means, the fact that that graph has those peaks in it, the ones that are highlighted in colors, tells you about the gas that gave rise to the light. So the stars are producing some of the light from this galaxy, but some of it is coming from the gas clouds. And though the light that's from the gas clouds, it's a little bit like sodium lights. You remember the grown-ups here will know sodium lights. Used to have them over all the roads, made that sort of yellow light that was a little bit hard to see. But what that tells us is that individual elements, when you put them in the right conditions of a rarefied gas and energize them, produce light of very certain, very particular colors. And sodium, of course, produces the yellow light. What you see from this is that we know that other elements that are common in all galaxies, and these distant galaxies like hydrogen and oxygen in particular here, also produced light of just very particular colors, several different very particular colors. And those are highlighted there in those, with those labels. And so what this allows us to do is a number of things. It allows us to say what kind of chemicals were there in those galaxies. And those chemicals, particularly chemicals like neon and oxygen there, they weren't made in the Big Bang. Hydrogen was made in the Big Bang, but those heavier elements were not. And so those have been made in individual stars and then blasted out into space in supernova explosions. So we can learn, not only are we looking 13.1 billion years into the past, but we're learning about stars that even preceded that, because they had to create those elements that we're now seeing in the spectrum of this galaxy. So we're learning about what elements are there, we're learning about the state, how hot they were, how fast they were moving around. And something else we're learning, which I hadn't mentioned so far, but I'm sure will ring a bell to many of you, is that actually we're looking in the infrared here. But if you were to make this kind of light in a laboratory, which we can do the same way that you can make it in a sodium lamp, you discover that these lines actually correspond to light that we can see. It's optical light. So what's it doing in the infrared? Well, of course, the answer is that it's been redshifted. This expansion of the universe that was discovered about 100 years ago now, it means that all the galaxies are moving away from every other galaxy, and the further away you look, the faster they're moving. So this one is moving at a speed, getting on quite close to the speed of light away from us, and it means that the light has been stretched out, all the wavelengths have been stretched out, and so although Webb is observing this light in the infrared, it's giving us a view of the optical light that you would have seen if you were much closer to this galaxy. So it kind of goes round in a circle there. We're actually observing the infrared in order to get the view that you would have had in the optical. So I thought that's interesting.
No, very interesting. And it goes to show again the importance of the different instruments that the Webb Telescope has. It's not just its infrared cameras able to capture some of these images and show us visually, I guess, some of the things that we weren't able to see before, but the fact that it has these spectrographs, these instruments that are able to not only collect the light, but then split that light up into their individual or constituent wavelengths to then look at those wavelengths and look at what those wavelengths tell us, and in this case, working out the composition of a galaxy 13.1 billion years away. So incredible stuff. We're already getting towards the end of our hour. So to make sure that we have some time for our audience to ask questions, I am going to finish with one last image, which was an image that was actually released today on the anniversary of a year of the Webb Telescope releasing its science images. And it was this stunning image that was revealed this morning. Are there any of our panelists who want to maybe describe what we're seeing here, or I guess the importance or highlighting why this image is so striking? So we've got the Rho Ophiuchi clouds. It's a star-forming region showing us, like we looked at before in the pillars of creation there, where these stars are being formed.
All right, I guess it's me then. Yeah, so this is Rho Ophiuchi. Most of the stars you can see in this image are stars about the same mass as our sun, so they're sun-like stars, with the exception of the one in the middle at the bottom, which is sort of surrounded by this golden light. That one is more massive, and it's almost finished forming. And what it's done is, as stars form from this collapse of a gas cloud, the gas gets squidged, and everything gets hotter and hotter and hotter, and eventually the star starts burning. So hydrogen starts fusing into helium, and the star holds itself up against gravity. And once it starts burning, it then sheds sort of the dust and the gas that was around it in the area where it formed. And this is what you're looking at here, this star, this sort of, all this golden sort of dusty gas is a cavity that's being caused by the star that's sat in the middle of it. And it's blown all this stuff away from it as it's suddenly starting to burn. It's almost like it's boiling it off to leave itself in this hole. What you can see sort of above it with all these long red filaments are areas where stars are still forming, and they're sort of emerging from the dust that they're forming out of, but they haven't got to the point where they've suddenly sort of blown stuff away from them just like you just sort of see one at the top there where things are starting to move. So yeah, this is quite different from the pillars of creation in that the star formation is still going on here. And these stars these newborn stars are very much shaping their surroundings still. So as they're burning, they're blowing away the dust cloud that surrounds them. And eventually that dust cloud may get to a point where it starts to form planets around these stars as well. So again, that process sort of happens. Disks around stars last for a few million years, maybe 3 to 5 million years. So these stars may have their own planetary systems in a few million years' time, which is very cool.
Awesome. A stunning image to, I guess, end our panel discussion, but we can open our floor to questions. So I think we might have no, we don't. Okay, I'm going to come around with the mic. So if anyone's got any questions, please do pop your hands up. I can bring around the mic and we can get our panel to perhaps delve a little bit into answering your questions. Please don't be shy.
How far can James Webb JWST see through the universe?
Right, okay, so I'll repeat. The question is, how far can JWST see? And it's a really good question, and we've been telling you it's a super powerful telescope, and so it can see much fainter things, certainly, than we've ever been able to see before. But an interesting thing about the universe we live in is that there's a limit to how far we can see. Any telescope that you could imagine can only see so far. Why is that? And it's to do with the fact that our universe has a certain age. It's about 13.7 billion years old, and that means we can never see more than about 13.7 billion light years away from us. And so when we're looking at those galaxies that I showed you, that it said it was 13.1 billion light years away from us, we're almost seeing as far as it's possible to see there. And much beyond that, essentially, it's as if there's an edge. And you're thinking, that sounds wacky. How can there be an edge to space? But what I'm really telling you is that the edge is formed by the beginning of time, because time started 13.7 billion years ago, we think. It means that you can't see any further. We never have seen any further. But we have seen light actually from very close to that edge, because the glow of the Big Bang actually makes light. It's not light that the JWST is sensitive to, but it is light that we've detected with radio telescopes even before now, actually back in the 1960s for the first time.
Thank you for your question. Any other questions?
Hi, my question's about Neptune. Is any of the heating due to tidal heating from any of its nearby moons?
So the question is are there tidal heating?
Is there any tidal heating going on?
Yes, right. So Neptune is the size, about 4 times the size of the Earth, so a pretty big planet. They have lots of moons, and as these moons orbit, the gravitational pull of Neptune will produce forces inside these moons, basically producing stresses inside the moon. So this is, tidal forces work both ways, right? You can have tidal forces on Neptune from the moons, and as well as tidal forces on the moons from Neptune, right? And say at Saturn, this is interesting, and also at Jupiter, you have tidal forces that heat up the interior of the moons, and actually it's capable of releasing material from those moons. Say Io at Jupiter, it's a really interesting example, is extremely volcanic. It's the most volcanic place in the solar system, surely by the fact that it's tidally heated by Jupiter. It's all these stresses going on inside the moon, basically creating volcanism on the moon. Same as Saturn with its moon Enceladus, which has not volcanoes like magma volcanoes, but instead it has geysers like you have on Iceland, so ice volcanoes effectively. So there are tidal forces, yeah, absolutely everywhere, and they do affect the moons and the planet. Yeah.
Thank you. Any other questions for our panel?
This is just on a massive scale that's almost impossible for my little brain to take in. But these images are simply beautiful. There is the most incredible order there. Predictability, we know where things are going, we can work out what they're made of. Does this just happen, or is there a design at work? Does this just happen? Is this chaos, or is there design here?
Shall I have a go? I mean, a really deep question, of course. I suppose in many respects, what we can say from our scientific studies is that it seems that the laws of physics that we have in our universe will lead to structures of this sort. And so we can largely, with some, some unsolved puzzles, but largely sort of understand how the galaxies have formed in the way that they have right from the beginning of the universe. And like I say, that does involve some pretty important puzzles that we're still working on, and going right back to the very early times of the Big Bang. And therefore we sort of can infer things about how the Big Bang itself must have operated in order to give rise to the universe that looks as we see it. What we still don't know, and what many scientists would like to ultimately be able to do, is work out a way that those laws of physics were somehow inevitable, that they are a consequence of even deeper and simpler principles, and that the laws that we see are not kind of slightly arbitrary. And by that, gravity is obviously really important, let's say, but it has a certain strength. It was a strength that Newton first sort of worked out. And if it had a different strength, then of course, then you would end up with a very different kind of universe, and possibly one much less interesting, possibly one where everything fell very quickly into black holes, and that was that. But we ended up somehow with laws of physics which just describe a really interesting universe with all this structure and richness. And what we definitely don't know is whether or not that somehow was inevitable from the outset, or whether there's a much deeper principle which has led to the laws of physics being just so. Or, there's another possibility which some people have speculated, which is that there could be many universes, and many of them may be boring, and it might be that only in interesting universes do life forms actually arise and intelligence arise, and therefore is in the happy position of being able to ponder these kinds of questions. And maybe in all the boring universes, no one ever asks the question.
Thank you for your question and the beautiful answer. Do we have any other questions that you'd like to ask our panel?
In what ways does the James Webb Telescope help us understand the chances of alien life being out there, or the likelihood of and level of sophistication of that life?
Okay, so the question was about whether JWST can help us determine whether there is or is likely to be life on other planets. We know of thousands of planets around other stars at the moment. Quite a large number of them are Jupiter-sized, so they're big gas giants, and they orbit very, very close to their host stars. They go around in instead of a year for us, their year is 4 or 5 days or shorter. And although there is the possibility that life on planets may take a different form to life that we are used to, and we know, looking at our own planet, there are huge amounts of organisms that can live in very peculiar places, like in volcanoes and the cold, deep oceans. We know, or at least we think we know in general, liquid water is something that is or should be required. So astronomers have come up with what's sometimes called the Goldilocks zone, or the habitable zone of a planet, which is the distance from the star where the planet would be warm enough to have liquid water, so oceans or rivers or whatever, in the way we see it in our solar system. And obviously this distance depends on how hot the planet is, how hot the star is. If the star's very hot, then your planet needs to be much further out. Otherwise, it doesn't have liquid water, it has steam. And similarly, if the planet is very cool, the star is very cool, the planet needs to be closer in. So most of our searches at the moment have focused around looking for small rocky planets. And actually, we had a slide that we've not covered around stars cooler and smaller than our sun, because we can see those. And JWST has taken spectra of quite a few of these rocky planets to date. They're mostly orbiting what I would call an M dwarf, a red dwarf, star cooler and less massive than our sun. And so far, we've found very little to indicate these rocky planets have atmospheres. So there is certainly a chance. However, and you're probably in a good phase for this, what we might need to do is wait for the next set of telescopes. So at the moment, NASA is discussing something called the Habitable Worlds Observatory. And one of the things they have suggested for this is that this should be able to image planets in a habitable zone around their star. Hour, in case anyone was wondering. So Habitable Worlds Observatory is aiming to image planets within the habitable zone of their star. And hopefully some of those images, depending on how we take them with the spectroscopy and perhaps in slightly different methods of spectroscopy where we split the light up in a different way, we'll be able to see if there are oceans on any of those planets. So that's very cool, but we're looking another probably at least 20 years in the future at this point. So our next set of observatories.
Lovely. All right, I think we have time for one last question if there are any other questions.
Questions on the observatory itself.
We can do that.
Yeah, from the first year's fuel that's been used, can you better estimate how long the mission's going to be? Because when it was launched, they were estimating 10 years, and it was such a good launch, they moved that out to somewhere nearer 20. So after a year of manoeuvring it, got a reasonable idea what the annual consumption is of fuel. Do you have a more accurate idea of how long?
So I've not heard any from the engineering team any precise figures. So 20 years is still the predicted lifetime based on fuel alone. That's of course not the only limiting factor for the observatory. We've had some impacts on the mirrors by micrometeoroids. So basically little space pebbles that's flying around, or even space dust that hits the mirrors. You know, the mirror's not enclosed like on Hubble. Hubble's in a big tube, right? And we can actually achieve a slightly cooler telescope by not having that big tube, but having it open to the space elements. And so having it hit by space pebbles is sort of a risky run, but so far there's not been an issue. So we're hoping for at least 20 years. You know, there is the opportunity to refuel the Webb spacecraft, but that basically has an exposed fuel cap. So, but the spacecraft to do the refuel doesn't exist yet, hasn't been designed yet. But you could design a spacecraft that flies out there, unscrews this cap, refills it, screws it back on again. You have another 20 years.
What a nice point to end on. There could be more. There could be more of Webb. First of all, I want to thank our panelists. Thank you so much for coming along today and sharing your insights on the Webb telescopes after its first year of science operation and sending back us some lovely images and data to really ponder over. Thank you all for coming along. I hope you all enjoy the rest of your day at the National Space Centre. And I think we should just end by giving our panel a big round of applause.